Hi, I'm Shizhe. I'm postdoc researcher at INRIA. I'll present our work, Think Global, Act Local, Dual-Scale Graph Transformer for Vision and Language Navigation. Vision and Language Navigation, VLAN for short, aims to train autonomous agents that can follow natural language instructions to navigate in realistic environments. Initial VLAN works mainly use fine-grained instructions. Such step-by-step instructions are cumbersome and less practical in real life. It's more convenient to use high-level instructions. This task, however, is more challenging as it requires fine-grained object grounding as well as efficient exploration in the environment. The existing VLAN works, however, are inefficient in exploration. They either rely on recurrent state or sequential memory to capture the whole navigation history, which are inefficient to capture the rich space-time structure. Moreover, these approaches only allow to make local actions. If an agent needs to backtrack n steps to a new location, it has to run the model for n times, which increases instability and computation. To address these limitations in this work, we explicitly build a map to support global actions for more efficient exploration. Our model is called DUT, Dual-Scale Graph Transformer. It consists of two modules, topological mapping and global action planning. At each step, the topological mapping module is used to update the map. Then the global action planning module uses the instructions and the map to predict the next location. We will compute a shortest path given the map to make local actions in the environment. In the topological mapping, we first encode the newly observed panorama via a transformer encoder. Both the view images and fine-grained object representations are considered in the encoding. Then we add new nodes and edges to the graph and also update the node representations. For global action planning, we propose a dual-scale encoder. It aims to balance the complexity on reasoning over large graphs and fine-grained cross-model matching. The coarse-scale encoder uses coarse-grained graph representations to predict a global action via a graph transformer. The fine-scale encoder uses fine-grained representations of the current location to predict a local action. We dynamically fuse the two encoders. We apply a two-stage training approach for DUT. In the first stage, we pre-train DUT with behavior cloning and two auxiliary tasks. In the second stage, we fine-tune the model with a pseudo-demonstrator, since we can obtain the shortest path in the training phase. We evaluate the DUT on both VLAN with high-level instructions and fine-grained instructions, including Reverie, Zoom, Room-to-Room, and Room-for-Room datasets. We use both navigation and object grounding metrics in evaluation. We carry out ablations on Reverie dataset. We first evaluate the proposed dual-scale encoder. The coarse-scale encoder achieves higher success rate due to the global action space. The fine-scale encoder, however, learns better stopping criteria due to the fine-grained representations. The dynamic fusion is superior than average fusion to combine the two encoders. We then evaluate the training algorithms. The auxiliary losses are more beneficial to the upper grounding compared to the behavior cloning baseline. Reinforced learning further improves the navigation performance by a large margin. And our proposed PID training is more efficient than the reinforced learning. Our DUT model outperforms the state-of-the-art methods by a large margin on Reverie and Zoom datasets. The absolute gains on success rate are more than 20%. Our model achieved the first place on VLAN challenges on ICCV 2021. For VLAN with fine-grained instructions, our DUT model also achieves better success rate on both Room-to-Room and Room-for-Room datasets. Thank you for listening. Please visit our project website for more information.